essentially what there's echo. No. Okay, I mute myself. That's good. Okay, so this is actually quite well aligned with the theme of the workshop. So for a very long time, we have been working on using only cameras to perform various tasks in autonomous driving. So for example, if we want to build a autonomous driving system, like here is a demo by Mobileye, we will need to use a single camera, especially on a lot of the existing assisted driving systems, to recognize the location and the trajectory of the other objects in the environment. For example, here we want to know that where the cars come, where the cars came from, and where they are going in the future. So this is quite an essential problem for autonomous driving. And my research has been centered around how we can use only cameras or vision-centric approach to achieve this task. And of course, the application of such vision-centric methods is not limited to autonomous driving. In many indoor environments, for example, when we want to build the home service robots, we also need this type of capability to recognize 3D environments through single camera in order to navigate and interact in the environment. So a very big advantage of doing vision-centric autonomous driving is very easy to scale up the data, scale up our algorithm with the data. So just basically by the recent discovery of large language model or large vision models, we can use our models to digest a large amount of data to perform certain tasks, like here, for example, to do image classification, segmentation, or detection. However, when we want to use the similar trend or use the similar experience to deal with 4D scene understanding, we face several obstacles. First of all, the algorithm for 4D scene understanding is usually very complicated. We need to know that how we can design the algorithm that can benefit from this large amount of data. And of course, when we want to label the videos or videos acquired in this vision-centric approach, we want to avoid many manual labels as much as possible, such that the model or the training can scale up together with the amount of data. Otherwise, the human labeling can become a severe bottleneck. So in this talk, I will discuss those challenges in 4 aspects. First, we will discuss how we can build the central algorithm for robust 2D tracking. Basically, how we can build the simple method for associate objects across the frame based on the existing advance in classification and localization. And on top of that, I will discuss how we can build the high quality semantic information or extract the high quality semantic information from those object tracking results. And of course, in the end, in the 4D understanding, we need to understand the association semantics, but as well as the 3D motion of the object. So let's start with something very basic in 4D understanding, which is object tracking. Usually in object tracking, we want to understand the 2D motion of the object. And this problem has actually been investigated in computer vision for decades. It's one of the major challenge in computer vision. And therefore, it also has many flavors during the development of object tracking. In particular, in our case, or in the case of autonomous driving, we are very interested in multi-object tracking. In this case, we usually do not know which object we are tracked in advance before we see the video. And then when we see the video, we know that we are going to track vehicles, different type of vehicles or persons. And therefore, we want to find those objects, even though we do not know the identity of those objects, and then associate the object or track the object within the video frame. So usually the current algorithm is following the paradigm of tracking by detection. So first of all, we will detect the object in each of the frames. So for example, we can use state-of-art object detector to locate the objects in each frame. And then when we analyze the object association or motion in the video context, what we do is first we use certain motion model to first propagate the object from one frame to the next, such that we can associate the objects on different frames together. And usually the motion model can be quite complicated. And of course, some simple heuristic like assuming the object will not move can actually work quite well. And after we have to propagate the object into the new frame, we usually perform some initial association, basically by aggregating the motion information and appearance information together. So the appearance information is also very simple. Usually we just compare, have certain model to measure the similarity of objects. And the hope is if the two objects are the same, then they will have very high similarity. Otherwise, their similarity will be low, even though the two objects may be of the same category. And in the end, with all those information, we will do like joint optimization. Use like either traditional method like on machine or use graph neural network to learn how to optimize the association of the object. So there has been a lot of criticism of object tracking algorithms. So one major problem is usually the pipeline is too complicated. There are many steps and many components in this algorithm. So therefore, this is the first problem I was thinking about object tracking. The question here is whether we can simplify the algorithm, especially do we really need to do motion estimation, and we really need to do association optimization. So a simple intuition tells me that very likely when humans do the object tracking, we do not require those information. For example, if you are driving on a highway and you want to follow the car in front of you, usually we do not need to estimate the motion, or we do not need to do a global optimization in order to know that the car is always the same in front of us. So in the end, it seems that when we do the object tracking ourselves, we are only relying on the detection. Of course, we always need to find objects we are interested in, and then just associate objects across different time steps based on the appearance. So therefore, one interesting question here is why does the appearance provide enough information in many of the existing models? So let's look at how we are learning to measure the similarity between objects first. So usually we have a lot of videos and in certain domains, and then we will ask a human labeler to label the data. For example, in this case, we have frames in a video, and then the labeler will tell us, okay, the black car is in the orange box, and the white vehicle is in the blue box. And then with this annotation, we can build our supervised training, either use triplet loss or use binary loss to learn the feature embedding to measure the similarity of the objects. The goal here is, again, if the objects are the same, then the feature embedding should be very similar. And if the objects are different, then there should be very far away in this feature embedding. However, there are actually several missing parts in this, in this learning scheme. First of all, there are many similar bounding blocks that are not considered in this procedure, which is kind of very wasteful because in reality, it's very hard to find, say, even if we ask the human to label the image, and ask them where are the vehicles, it's actually very rare that two persons will exactly agree on the same bounding block location. Usually there is some a shift, just because a human can usually label the object differently. And therefore there can be a very big difference even before human labeling. However, when we considering labeling the objects, or when we consider learning the similarity, usually we do not consider those similar objects. And another problem is we usually do not considering the misleading areas in the background that it can, say, become false positive in the association. And therefore, based on those observations, we propose quasi-dense matching. Basically, the idea here is instead of only comparing the bounding blocks appear in the ground truth labeling, we try to compare the bounding blocks that are likely to be the objects. Basically, on each image, we extract all the regions of possible objects, and then do a joint comparison or do a joint learning across the comparison of all those regions between two frames. So if this sounds familiar to you, so this also inspired by the design of the 16 detection model. For example, here is the model of faster RCN. Basically, when we want to detect vehicles on the image, we will first pass the image into some base model and then pass it into a recent proposal network to find out possible object locations. And then after that, we will pass the object feature into a bounding box to do a refinement and then determine the class of those objects. So we can basically reuse the recent proposal result and then pass them into another embedding hack, which aims to learn the similarity of objects. And in the end, we can just compare all the possible locations in contrast learning, and then learn the embedding hack, which will achieve our similarity learning purpose. So at the testing time, we can just use the nearest neighbor who measure the similarity between objects and then find out that which are the closest objects in the embedding space and then associate them together. So even though we are only using the feature for doing association, so here is an example of the tracking result. So you can see that even though this result this thing is quite complicated, but our result is still very reasonable, even though the objects are appearing, disappearing, but our method can still track them very well. And of course, another big challenge in object tracking is usually we are only using very limited data, and therefore a lot of those tracking methods cannot learn from large amount of data. To address this problem, we introduced V200K several years ago. It's currently still the largest open driving video dataset. It contains 100,000 videos with very diverse scenarios and different time of day, and then also different scene types. So in particular, we use the dataset to construct a new benchmark on object tracking and the segmentation tracking. So you can see that it depends on how you measure the dataset scale. So it's usually one scale, one order of magnitude bigger than the existing tracking dataset. So combining our simple tracking method with the large scale data, we can actually achieve very performant object tracking results. So here is an example on the V200K in the highway scene. So you can see that the tracking is actually quite reliable, especially for the objects that are nearby. And because of the diversity of V200K, we can also track objects very reliably in some challenging scenarios, like here in the night scene. You can see that the mouse method is tracking the vehicles and the riders on the road, and pedestrians are very well. So if I tell you that our method is doing very well on V200K on our own dataset, that may not be very convincing. So we also test the result on another dataset called Waymo Open Dataset, of course released by Waymo. We find that the tracking method can actually work quite well and then still benefit from the large amount of data available in the dataset. And of course, this is very good. So we are able to get very good tracking performance on the common objects. However, in the end, we hope that we are able to track every object in different scenarios. This will be beneficial for the universal application of object tracking. At the same time, even on street scene, there are many objects in the long tail distribution or very thin objects that we want to track, and they may actually become some big become the source of danger on the street. However, when we want to track every object, we actually run into some trouble. So first of all, when we do object tracking, usually we rely on the accurate classification of the object. So in the traditional multi-object tracking dataset, usually we only have a single type of object like persons or vehicles. And in terms of, say, on street scene, say V200K, we first detect objects and then classify that whether they are persons or they are vehicles. Then after we have those category information, we will just associate objects within the same category. It doesn't make sense to associate person and the vehicle because if they are different categories, then they have no chance to be the same object anyway. However, if we consider the long tail distribution, then the classification actually becomes very noisy. And then you filtering the association candidates through the category information actually become quite challenging and can actually become cause a lot of false. And therefore, this actually creates some challenge here. At the same time, we also observe that we actually do not need exact category in order to do the filtering. We only need to know that whether the two objects are in the same category or not. So this is actually very interesting because not only this is easier to learn, but also help us to extend the checking of our filtering scheme into even the unseen category. So it's possible to generalize say, if we have a classifier to check whether two objects are same category or not, then since we do not restrain ourselves into a particular category, then we can easily extend or generalize this method or model into the unseen categories. And in the end, we can also postpone the decision of category information if you still care about it. And when we have multiple samples of the objects from multiple frames, then we can come back, see that given all the information we have collected about objects on the videos, how we can better determine the object categorization. And therefore, we designed a new module called class exemplar matching. So the goal of this method is just to match the objects of the same category together. It's actually inspired some previous ideas on exemplar SVM to say use an example or use use an image to determine what will be a good classifier for the category or for measuring similarity of objects. Then after we train this module, so on the real video, we will first locate our object or locate possible objects. We find that even though the classification can be quite noisy on the long-tail distribution, but to determine the localization of the objects actually can be quite reliable. And then after we locate the object of interest, then we will use our module to split the candidates into several groups. So in the traditional tracking, basically those are say persons or vehicles. And here we do not know the exact category name, but we only know that very likely they are the same category. Then we can do association within the same group. After that, we can determine, so for each track, what will be the category after we've seen many examples of it. And of course, we can use this module not only in our own tracking method, we can also use it for the previous tracking method like deep sort or Tracker++. And we find that on the long-tail object tracking dataset, we can have a significant improvement in association. And it's more interesting that even on scripting, say on P200K, we still observe a significant improvement, mostly because that on P200K, we also, even though we only have 10 categories, but they also follow a long-tail distribution. We have many cars in the data set, but not many buses or trains in the data set. Okay, so far so good. Basically, we have a very simple tracking method, and then which based on appearance matching, and then we can use it to extend it to track every object in the data set. So even further, we hope that we can basically relieve the requirement of training labels in video because it's just super expensive to labeling the tracking labels, to labeling the object tracking. So for example, on P200K, when we label the object tracking on 100 frames, it usually takes 8 to 10 hours to label one video with 100 frames. So with the requirement or with the design of this appearance only tracking, we find that we can actually use the data augmentation to synthesize the tracking pairs. The idea here is, say, if we have we image with object detection results, then we can just transform the image by, say, resizing, scaling, or translation, such that we can have a new frame. And then because the augmentation follow a fixed path of transformation, we can also know that where the object will be after those transformations. And then we can use this way to synthesize new tracking pairs. So here are the comparing results. So one video is trained with full supervision. The other video is trained with only the synthetic tracking pairs. So you can see that it's actually very hard to tell which is which. And indeed, in quantitative evaluation, we also find that the performance is actually very similar on small scale data sets like M1T17. So another benefit of only relying on appearance is it can be very robust to different type of 2D motion. So here we do an evidence study on MOT17. So on MOT17, all the videos are 30 frames per second. And then we have some very performant method which is based on motion estimation or based on some strong motion models. And what we do is we sample the frame rate for the videos. Basically, it means that we accelerate the motion of every object in the video. So you can see that the motion that is tuned for 30 second, 30 FPS video actually degrade very fast when we accelerate the video play. So on the other hand, the appearance only method can actually still be quite robust in this domain. Of course, if we know the frame rate of the data set, then we can always tune the proper motion model for this particular data set, but that's basically defeat the purpose of designing a robust tracking method. So this is very nice. This means that if we want to track the object like in the long-tail distribution or at a larger scale, we can even avoid labeling like the video data and only rely on video data augmentation based on single frame. So even further, beyond the everything mode, we also hope that we can track objects in open vocabulary. Basically, in the open vocabulary setting, we do not have, we even want to test the tracker on the video with unknown or unseen categories in the training time. The goal is to generalize the model from the seen category to the unseen categories. And of course, as usual, we have to look at the several components in the tracking in order to see that how this open vocabulary setup will affect each of the components. So for classification, we actually follow some like existing technique in the classification and detection. Basically use a click distillation to generalize the classification or generalize the category prediction embedding by using a joint embedding of text and image. So on the other hand, we still need to think about that how we can generalize the association or how we can train the association for the long tail for the unseen objects. And especially we may not have a lot of training data for each of the category we care about. So of course we can still use data augmentation that we discussed. Another opportunity here is we also have this AIGC. Basically, we can synthesize new images, realistic images based on certain instructions. So what we did here is basically follow the trend of the AIGC and see that how we can use it for the purpose of generating the tracking ground, like better tracking ground truths that can go beyond data augmentation. After all, even if we can do data augmentation, the images are still look pretty similar, and we do not have, say, a lot of variation in the image appearance. So what we can do here is, so given an image, we assume that we have certain distribution and also a mask for the targeting object. Then after that, we basically take out the object mask and then put it on a blank image. Then we use the text to generate another image while retaining the targeting object. So this is very similar to image painting, but this is the reverse way. Usually in image painting, if you have the object mask, you want to remove it and then paint some other background or something. But here we want to retain the object and then paint the other part of the image. Then of course, we can formulate this as a conditional diffusion process and then generate the image based on all the conditions we have here. And as long as the image satisfies all constraints, then we can still retain the ground truth labeling between the source image and the target image and use it to train our tracking model. So in the end, we can build a variation of our appearance-based tracking model based on those insights. So what we found quite interesting here is, even though that we do not train our method on any of the video supervision, our method, the result can actually be better than the previous method that is trained on the we trained with the video labeling ground truth. So I think this is very interesting. This says that if we cannot say label hundreds of thousands of video for each targeting category anyway, and then especially in the long tail distribution case, probably we can just rely on like generative model and data augmentation to train the tracking or train appearance-based tracking, which can give you very good performance. And of course, more details will be presented on Tuesday in the afternoon poster session. So a quick summary is basically we find that appearance tracking is very easy to scale to diverse environments and very easy to generalize to new concepts. And of course, it's also very robust to different motion patterns, and it can be trained with only images. And also there are many ways that we can design to synthesize the data and then train a more powerful tracking model. So this is all good, but in many cases, we do not we want more than like responding box tracking. Sometimes we hope that we can also have like image segmentation tracking. However, image segmentation tracking is even harder to label, and therefore it's very hard to scale up if we always need to rely on ground truth label. So one question here is whether we can avoid the labeling the mask altogether. So it seems to be possible because there has been some research on image-based VCAD supervised image segmentation, and they show that the very good performance. However, if we directly use those image-based VCAD supervised segmentation on video, we can see that the temporal consistency can be a big problem. Actually, in this scenario, temporal consistency can both a big challenge, and it can also be a blessing. It's a big challenge because if we are not careful, a lot of artifacts that is kind of invisible on a single image can be quite jarring on the video. Just because like if there's any small artifacts, and in the video domain, our vision perception system will be more sensitive to those. And at the same time, of course, we can think about how we can use temporal consistency as additional cue or self-supervision for us to train high quality videos in sense application. So you may a common technique of using temporal consistency can be optical flow, but here we hope that we can deal with or we can learn from large amount of unlabeled data in the wild. And in those scenarios, if the optical flow method may have unpredictable results. And therefore, instead of relying on optical flow, we design a very simple patch matching scheme. Basically, for each patch in the first image, then we have assumption that it won't be go very far away in the next frame. And then within this range, like say here with this from one patch, we try to search for 5x5 range in the next image. And then within this range, we try to find some top K matches. Basically, those are the most similar patches to the original patch in the previous frame. And then our heuristic is very simple. We just say that, okay, if the two patches are very similar, then very likely they should have the same semantic meaning. And therefore, we can use this as additional constraint to train our VCAD supervised instance application. And here is a result demonstration. So the first video shows that the result of only using image-based VCAD supervised application and use it on video. And the top right shows the result of using a fully supervised mask to train our model. And then the bottom one is our model trained on only bounding box. So if we inspect closely, you can see that there can actually our method can benefit significantly from the temporal supervised temporal consistency supervision. And even in quantitative evaluation, we find that there's a very big improvement if we can introduce the temporal consistency to help us supervise the video instance segmentation. And here is like a longer video result. You can see that in this video, the segmentation of the persons are actually quite good, even though there may be some small artifacts on like some challenge scenario, like the frame of the glasses. It's worth noting that when we train the model, we are only using bounding on single images. We do not use any mask on video or like images. So, but we can still get a very high quality video instance application like this. So I think this also quite interesting to see that whether we can scale up similar method or the similar approach on even larger scale data to see that whether we can really generate a lot of like video mask without turning to like, expensive human labels. And more results will be presented on about paper will be presented on Thursday afternoon. So far so good. We are able to analyze object motion on a 2D view domain, and we can also give you very good semantic information without requiring lots of human labels. And of course, when we talk about 4D scene understanding, we have to elevate from 2D to 3D. And when we talk about like 4D scene understanding and analyzing the dynamic objects, one big challenge can be boiled down to like single image depth perception. So this is basically an impossible task in the sense that here geometrically this is a highly ill-posed problem. But this is the real problem we want to say predict the depth for the moving objects in a video. Because in those scenarios, we cannot turn to a structural motion or triangulation to find out the 3D location of the object, even in the video domain. So we have to basically use a single frame to estimate the depth of the object. And therefore, we also spend some efforts to see that how we can build a basic method to do the single image depth perception. And the only way we can do this is we can learn a very strong bias from the training data to test data. Basically, we may see that we have to estimate how big the sofa is and how big the different object can be, such that we can estimate its depth in the testing time. Most of the current methods rely on like learning the bias or learning this prediction on single pixel domain. What we hope to do is instead of only like predicting based on each pixel, we are thinking that whether we can learn the bias based on each group of pixels or at the level of objects. So therefore, what we do here is we first look at meaning or similarity of the depth. So and then learn on each of the group of the pixel. Do this grouping. We do not rely on any of the like mask annotation of the image. We are only using the depth information to like say to train the grouping. And therefore, the model will learn that how we can group the pixels such that we can better predict the depth for the image overall. And if you are interested in the model itself, here is the rough the general design. Basically, we have a bottleneck layer which tries to map the embedding of the like the image into some space, and then similar to the discovery, we try to group the pixels together. We predict or decode the feature representation. So it's actually very encouraging to see that even though we only have a single image to predict the depth, but on the image actually on an outdoor scene, like say when we want to drive our car, the prediction actually is working quite well. And here is a comparison to the LiDAR. You can see that it's actually the depth is actually very good. And it's very hard to see the obvious problem in the depth prediction. And of course, because we are predicting for each pixel on the image, we can predict the denser pixels. We can predict denser depth. And here is another view of the depth prediction. So, well, again, see that the single image depth perception is actually working quite well nowadays. And probably can, in many cases, it's very hard to see the difference between the predicted depth and the LiDAR depth. Well, if you are interested in more information, our group member will present the paper again on the Tuesday afternoon. Okay, so in the end, we hope that we can put everything together to have a full 4D scene understanding of the environment and to achieve, say, autonomous driving application. Of course, a major challenge or major application or major task we want to do here is to predict the like 3D location of the vehicles or other objects only through monocular cameras. So at the very beginning, we build a simple baseline. Basically, we first detect the objects and then predict their 3D location and then rotation angle. When we have multiple frames, we use our tracking method to estimate to associate objects together on 3D domain. And then when we have multiple frames, we will use certain 3D motion model to track down to even further enhance the tracking of the object. So here you may ask, so why I hesitated to use motion on 2D domain, but happily use motion in 3D domain. There are two reasons for this. One thing is on 2D domain, the motion is quite erratic in the sense that even for a stationary object, it can move randomly in the 2D image because of the camera motion and also because of the perspective distortion. Or in 3D, the motion is much more regular. So if very likely the object is just moving at a constant speed or with acceleration. The thing is like understanding 3D motion is inevitable for some downstream application anyway. For example, if we want to predict the vehicle model to predict the trajectory. And even further, we find there are many good usages of 3D motion. For example, in some challenging occlusion case for tracking, like here, let's say we have three objects in the image, and then in the frame, the second object disappears. Then we basically can keep sliding it in the 3D domain and see that constantly check whether it go out of frame or if it should reappear in the frame where it can be in the image, we can achieve reliable tracking. So here is demonstration of the result. So we have two views here. On the left, we have the perspective view, and on the right, we have the top-down view. So we can see that in this very crowded intersection, our model is actually predicting track the vehicle quite reliably. On the left is we see the tracking very reliable, and on the right we see that the layout of the street or layout of the vehicles are accurately predicted. And of course, benefit from the large amount of data, we can also do tracking very reliably in the next scene. So even further, when on many of the modern autonomous vehicles, we have not only single frame, we have multiple frames, which provide us a surrounding view. They actually create another opportunity because in the traditional tracking, like object disappearance and reappearance can be quite a challenging scenario. However, when we have panorama view, then the disappearance will become less likely to happen unless the object is blocked by something else. If an object go out of one frame, then very likely it should appear in another frame. And therefore, when we have multiple frames, what we do is we will first track an object across multiple views, and then track the objects across different time steps. And we find that can actually work much better than considering each individual frames. And of course, this can also work if you only have multiple frames, not necessarily covering the whole surrounding view. So what we found is we are actually witnessing significant progress in the in monocular 3D object tracking. So last year we found that we can achieve very dramatic improvement by combining our depth estimation and the 3D tracking together. And this year, when we consider panorama view, we observe that we can make another big progress. So with the advent of foundation model in image analysis, we may be able to push the progress of monocular 3D object tracking even further. So okay, and this is actually very encouraging for the vision-centric approach for autonomous driving because we are basically seeing the convergence of the LiDAR-based approach and the vision-based approach. So if we can have full monocular tracking results similar to and find that LiDAR does not provide literal information, then probably that's the time we can have full vision-centric autonomous driving. Okay, in the end, here's the brief summary. So we hope that we can scaling up the vision-centric approach for autonomous driving with less hassle. Basically, we hope that our model can scale up with the data, but without requiring significant amount of manual labels. And we introduce the 2D tracking, which can track objects based on only appearance, and then can track of course, we can do high quality object tracking with only without turning to the mass field prevision. And also we can achieve nowadays a very competitive 3D perception from only monocular views. Okay, this is a good time for some questions. Thanks a lot for attention.
Thank you, thank you. Yeah, we have time for a few questions.
Impressive result, because, yeah, congratulations. I have some questions. Do you have any like failure case analysis for appearance based tracking protocol? How does in terms of like weather data, maybe extreme lighting changes and large viewpoint changes? And how do you see that will affect something like especially?
Yeah, do some analysis on the method, especially on the large scale data. So first of all, we found that the tracking method is doing very well for the say for the yearly carbon, which means that, for example, when we look at the video, we even though the video may have like a 20 cars, usually our attention is on the several cars that are immediately in front of us. So for those objects that are closely related to the vehicle, we find that it's very hard to find every those scenario. Of course, part is thanks to the reliable detection models that we are having nowadays. And in many of the failure cases, is for the faraway object that's very small or has very complicated reappearance pattern or occlusion pattern.
Okay, thank you. All right, awesome talk. I don't know how you simplify the tracker and sort of ask why do we need X in the tracker? Like the logical next step is why do we need tracking? Do you have any sort of thoughts on sort of can we at some point replace tracking altogether with something?
Yeah, it's interesting. I feel that this question is similar to 20 years ago. People always ask, why do we need segmentation? So, well, let's say naive answer would be it's just a part of the basic vision function. And we hope that we can achieve that as a verification that, okay, our vision with our artificial vision system can also do something that a human can easily do. Because that understand is very critical, especially from a vision-centric approach. And the approach we take, our belief, first is in 2D, and then go from 2D to 3D. I was thinking whether we can directly go from 3D, basically say just project on this 3D there. I would say that it's very helpful for myself. And so far, we have done that path just because the current pipeline is very hard to beat.
Awesome. Thank you.
Okay, let's.
Oh, we have any question online?
No, so there are no questions.
Okay.